Okay, let's start. Thank you everyone for joining. So today we have one of our new postdocs at the Institute, Hannah Brinkman. So she started a few weeks ago in the group of Connie Aerts. She is 99.99% of her PhD is finished. So it's the 0.01% that she still has to do. And then it will be Dr. Brinkman. And she will talk about the work that she did in the past 4 years, and it's short-lived radioactive isotopes from massive binary stars. So please, Hannah, you have the floor.
Okay, so I hope everybody can hear me. Let's see. So as said, I did most of my research for the past almost 5 years on short-lived radioactive isotopes and the early solar system, where we focused on the source of massive binary stars. In this case, short-lived is short-lived on a stellar timescale, so these are isotopes that live from a few 10,000s to a few mega year. And here is a list from a recent paper from my PhD supervisor, where she gave a list of all short-lived radioactive isotopes that can be interesting to use cosmochronology to determine where everything that formed the early solar system came from. And my research has focused on this little part, Wolf-Rayet stars, where we focused on aluminium-26 and calcium-41 and chlorine-36. And so these isotopes get produced in massive stars and are expelled through winds and through binary interactions. And these isotopes are important, therefore, for the early solar system. As you can see in the list, it says proton captures for aluminium-26, which is produced in hydrogen burning, and it says neutron captures for calcium-41 and chlorine-36, which is produced in helium burning. So here we see parts of the nuclei chart where we see the production channels. So here is magnesium-25. We get a proton capture, we form aluminium-26 over here. Aluminium-26 has a ground state, which has a half-life of 0.72 megayear, and an isomeric state, which is like an excited state, with a half-life of 6 seconds, so we basically ignore that. And then later on it can get destroyed in the stellar interior by proton captures and by neutron captures. Then here there is chlorine-36, which is produced by neutron capture on chlorine-35, and then destroyed also by neutron captures, or it decays into a stable isotope. Just like here, aluminium decays into the stable magnesium-26, calcium-40, neutron capture, calcium-41, and again, either the destruction through neutron captures or via decay into potassium. The start of the project was on aluminium-26, because this is produced in hydrogen burning, so that's the easier isotope in this case. So as said, aluminium-26 has a half-life of 0.72 megayears, and therefore it can be considered as a fingerprint of local ongoing nucleosynthesis when the early solar system was formed. So it is a source very close to the creation of the protosolar nebula. Also, aluminium-26 is interesting because it can be a potential heating source for planetesimals in the early solar system, which has to do with if you have a lot of aluminium-26, you get a lot of heat, and your water evaporates. If you don't have a lot of aluminium-26, you don't have a lot of heat, and your water stays. So this is how some people consider, like in the papers by Lichtenberg et al., how you get the difference between rocky planets and water worlds. The other thing that's very interesting about aluminium-26 is that it's actually observable. So we can, through active decay of aluminium-26 into magnesium-26, we can see these gamma rays, and they have been seen by the Compton and integral instruments. The other way to observe more or less aluminium is through its decay product. So this will be a magnesium-26 excess in, for example, stardust grains from Asian stars and meteorites that have been dated back to the early phases of the solar system. So here there is a map of the galaxy, and here you can see the gamma rays from aluminium-26 are concentrated in the galactic plane here, with a big load of them in the inner galaxy, but also here in different areas, especially here at Orion, that have been determined to be OB associations, so these are clusters of massive stars. And this context, massive star means 10 solar masses and up. The interesting about massive stars is that they can basically produce two separate groups of the aluminium-26, first through their stellar winds, and then all the way to the end of their evolution through the supernova ejecta. By the way, if there's anything unclear during the talk, just let me know, because I've been looking at this for almost 5 years, so everything is very obvious to me, and it might not be obvious to others. So for my research, I mostly worked on theory, so we did simulations with the MESA Stellar Evolution Code version 10,398. And for the first part, because aluminium-26 is produced in helium burning, we only evolved the stars up to the onset of carbon burning, because then you have had the mass loss and you're good. In this case, we evolved the grid of stars was between 10 and 80 solar masses, and we used solar metallicity with the mixture of Asplund et al. So here are the results. So first of all, there is 4 studies from the literature where you can, and then the blue line, those are the results from my single star models. So we have some outliers over here from Ekström et al. 2012, which is due to an enhanced stellar wind. They explain in their paper that for better convergence of these models, they had to boost their stellar wind a little bit. But in the overall trend, the results from the single stars look pretty similar. So this gave us confidence to go on to the next step, which is binaries. So why did we want to look at binaries? First of all, as you can see in this figure from a review paper by Duchenne and Krauss on multiplicity of massive stars, you can basically see that the higher you go up in stellar mass, the more likely you will find a star with a companion, as seen here with early B and O stars. So these are the stars we're looking at. They have almost always a companion or even more, and the multiplicity factor is about 90%, 80 to 90%. So these stars are just not alone. So in 1995, which is a long time ago, it was suggested that binary interactions can lead to an enhancement in your aluminium-26 yields as compared to single stars. So this was done, unfortunately, only with 2 models. So what we did was we went back to these models and we made a lot more of them. Let me see. So why does this work? So first of all, when mass is transferred from the secondary star, from the primary star to the secondary star, during Röhrschlope overflow, as you can see here in the schematic, the mass is lost from the system, which in the vicinity of the secondary star. And in our research to avoid a lot of complications, we used fully non-conservative mass transfer, which means basically that all mass goes from the primary to the secondary and then out. Therefore, in this process, the primary star loses its hydrogen-rich envelope and then exposes the helium core, and that is exactly the spot where the aluminium-26 is synthesized. Which means that the layers where we have these particular isotopes are brought closer to the surface, and then the stellar winds that occur after and during helium burning will move this material into the interstellar medium. So what we see, and here you can basically see what kind of difference it makes. So this is on the left side, there is the mass evolution of a 20 solar mass star. It is been modeled with a companion of 18 solar masses, so the mass ratio is 0.9. And on the right, there is the surface abundance of aluminium-26. And basically here, the single star is in blue, so on most of the time, nothing happens, and then it starts losing mass. And then you see here with the single star that nothing, no aluminium, and then by the time the star starts losing mass, so at 8.5 mega-year, you see that the aluminium surface abundance goes up, and this is what gives you your yield. However, if we then put the stars into a binary system with a period of 2.5 days, which means that the mass transfer will take place on the main sequence, also known as case A mass transfer. You can see that you're here on the main sequence and your stars start losing mass, more and more mass, and then it goes down to the stellar winds. And so the difference is that even though you can see that the increase in the surface abundance happens at approximately the same time, it goes up a lot more. So this will increase your stellar yield. And then the last one, which is a case B system at a period of 66.2 days. So case B means that the mass transfer happens between the end of hydrogen burning and the onset of helium burning. This is a phase where the star rapidly expands, so there's a lot of mass transfer possibilities there. And again, you see the same mass transfer happens, the mass of your star goes down very quickly and then slowly goes down. And as you see here, the surface abundance rapidly goes up and you have a higher surface abundance of aluminium-26 by the end of your simulation. So this is one of my favorite diagrams, and maybe for other people absolutely terrible. These are Kippenan diagrams that show the interior of the stars. So very quickly, mass of the initial, the total mass of the star in mass coordinate and the time. The green areas are convection, where the blue areas here indicate overshoot. The red dotted line here is the size of the helium core. The blue line here at the end is the size of the carbon core. And here the red parts is where you have semi-convection. So, and on the color scale is the abundance of aluminium-26. So what you see for the single star, there is production of aluminium-26 in the core. It even starts decaying a little bit already, you see on the color scale, and especially like in this area, you can see that the place where the core has been retreated for the longest time, you get a gradient. Here the convective envelope dredges up the material deeper in, so you get aluminium-26 in the envelope, and here you also see that during helium burning, you get destruction. So at the end of helium burning, there is no aluminium-26 left in your core, which is important later on if you want to look at the supernova, because then basically you have a entirely newly synthesized aluminium-26. So here you see again the binary system at 2.5 days, and what happens here is that you move already into the envelope during the mass transfer, then you have another rapid mass transfer phase, and you actually get a lot deeper into the star, and a lot deeper into this area where we have all the aluminium-26 present, and you see here especially at the end. However, if we go to more massive stars, so this is a 50 solar mass star, basically it stops making a difference. Again, we have a single star, which already lost quite a lot of mass when we started the plot, and it just keeps losing mass and more and more and more. While for the case A system, you see again, it loses mass, but at the end of the run, it's actually not that much lighter compared to the single star, while if we go back here, actually there's quite a big difference in final mass between the single star at 20 solar masses and the final product of the binary evolution. So, and also here, actually the case B system looks pretty similar to the single star. And the same you can see in the surface abundance, even though for the case A system, the surface abundance goes up earlier. In the end, it looks all pretty much the same. So at some point, the binary interactions lose their impact on your yields. And this is also seen here in the single star and the case A system, both of 50. They look actually pretty similar. So even though they're here, this vertical bit is your mass transfer phase, in the end, there is not that much difference between the stars as you saw earlier for the 20 solar mass system. So Altogether, we did masses actually between 10 and 80 solar masses with steps of 5 solar masses. We ran periods between 2 to about 100 days, and all at a fixed mass ratio of 0.9. And then the general results are which we refer to as the effective binary yields, which basically means we assume a flat period distribution. We sum all the yields per set of binaries and divide them by the amount of periods we simulated. And you can actually see here that if we look at 10 solar masses, we get a giant increase in the final yield. And it stays more than the single star yield till you reach about here, which is around 40 to 50 solar masses, and then basically the binary interactions lose their effect on the yields, so you get a comparable yield to the single stars. So the conclusions for aluminium-26 are binary interactions are important for initial masses of the primary star between 10 to 35 solar masses. And above 35 solar masses, the strong stellar winds and the binary mass transfer have basically a similar effect on the yields. However, because you can get this increase in the yield, binaries can have a strong impact on the aluminium-26 contribution to the early solar system. But when you compare it to the galaxy, the contribution from stellar winds and binary interactions is likely very minor for the galactic aluminium-26 budget compared to the contribution of supernovae, because those yields are like a factor between 10 and 100 higher than the wind yields. So after this promising first result for aluminium-26, we went on to expand the nuclear network we looked at. So we created a network of 209 isotopes to cover the production also from chlorine-36 with a half-life of 0.3 megayear, calcium-41, which has a half-life of 0.1 megayear, and also we looked at iron-60, which has a longer half-life than the other three of 2.6 megayear. And while we use chlorine-36 and calcium-41 to further constrain the sources of these short-lived radioactive isotopes for the early solar system, iron-60 mostly is there to check if it's not there. Because what we see in the early solar system is that the ratio between iron-60 and aluminium-26 is different from what is expected from supernova simulations, but also from gamma rays, because like aluminium-26, iron-60 can be detected in gamma rays as well, and you get a different ratio. Therefore, we are looking for a source that can give us aluminium, but no iron, to make sure that that we can match the ratio in the early solar system. So in this case, we did not look at binaries yet. We decided first to expand the network up to core collapse as well, and introduce the effects of rotational mixing with initial rotational velocities of 0, 150 and 300 kilometers per second, and we evolved the stars to the core infall of about 300 kilometers per second. So then you get this, and these are very busy plots. So basically what you can see is that for aluminium-26, there's a few differences, because compared to the single stars from my first research and single stars at 0 kilometers per second from the second one, this is because these two stars didn't evolve all the way to the endpoint we wanted, and in the new set of models they did. So this causes a slight increase here. We also developed in the first part of the research something that we called semi-numerical binaries, where we basically just assume that once the star reaches the same, the radius of the star becomes similar to the Rush-Lobe radius, it loses its entire envelope, and we just sum up all the aluminium-26 in the envelope to get a bit of an estimate of how much aluminium-26 there could be there. And basically, these are all the same for the different rotational velocities. The actual binary models will come later. And again, we compare to the literature. And if you look here overall, most models give approximately the same yields and the same value, except here in the lower mass end where the models by Limongi and Kiefi from 2018 stand out a bit. This is because their models were configured slightly differently. They moved a little bit more red, and therefore they entered a regime of stronger stellar winds, which leads to a stronger mass loss, and then, well, your yield just goes up. And this also shows that, well, there are still parts of the stellar evolution that we might not fully understand, which greatly impact the yields and actually have a comparable effect to the binary interactions. So be careful there. So this is the first results for chlorine. So again, the yields are very, very low at the lower mass end. And then here, once the stars start moving into the Wolf-Rayet regime, so they get very strong stellar winds, they all become approximately the same, where the effect of the rotational mixing is mostly on the onset of these stellar winds. And again, here the yields are a little bit more chaotic, but in the higher mass end, at some point they all start to become more or less the same, which is good. That means the models agree with the simulations of other groups that use other settings for their models. Yes, this is a different one. So calcium-41 looks almost approximately the same as chlorine-36. This is because they've been produced in the exact same phase. So they're all produced in helium burning and expelled at the same time. So it would be weird if they behaved a little bit differently. So mostly it moves up and down a little bit, but that is due to the production. So and here you can see why this is happening. So this is again a Kippenhahn diagram. Now the x-axis shows the time till the core collapse. So there's hydrogen burning, helium burning, and you can see the production of calcium-41 here. And well, there's quite some production of it here in the later stages in the core. The only problem is that's not coming out of your star at all. So for the 30 solar mass star, you see that the mass loss happens, but it does not reach the processed area. While if you look at a 50 solar mass star, you actually start dipping into this region where your calcium-41 is produced. Mind that these both are non-rotating models. So here's iron-60. So basically here it says -40. This is just numerical noise. You can't do this precision. So basically no iron here, nothing here, and a very, very limited amount, like 10 to the -10 solar masses of iron-60 in the winds, which is negligible. And you see the same results from the other studies, where again the final yields, the final wind yields are all around 10 to the -10 solar masses. Okay. So then the next step. What about the early solar system? So for the early solar system, we know how much aluminium-26, calcium-36 and chlorine-36 and calcium-41 has been present based on meteoritic samples. So in this case, what we did, we were using a dilution model. So basically what we say is like, these are the yields from the massive star. We divide it by some factor, F, the dilution factor, and then we start decaying and hope that we get to the early solar system composition. So first step is calculate the dilution factor, which we use aluminium-26 for, where we assume that the initial amount in the early solar system was 3.1 times 10 to the -9 solar masses. Aluminium-26 is used in this step because it's the most well-constrained of the three. Then we calculate the delay time, which means the time between the ejection from the source to the injection into the early solar system. This time is the ratio of the radioactive isotope over the stable isotope in the early solar system. So this is in the ejecta, and this is in the early solar system, times the half-life of the radioactive isotope, yes. And for this case, we use calcium-41 because it has the shortest decay time of the three isotopes. Then we get, when we then match the early solar system, we check the other isotopes and reverse decay the aluminium-26 to see if it still matches, and repeat this process a couple of times until we find a value that converges more or less, and then we apply the final dilution factor also to chlorine-36. So what happens then is something like this. So here is a 40 solar mass star, a 60 solar mass star, and an 80 solar mass star, all. And the color bands, so here there is the horizontal line, so this is aluminium-26 over aluminium-27, where aluminium-27 is the stable reference. Yes, there is an error bar on it, it's just not visible. Then there is the other ratio is calcium-41 over calcium-40, which is here on the bottom, which has a larger error bar. And again, there is chlorine-36 over chlorine-35. It's up here. And then we have the three different rotational velocities. So here we can see that it's the ratio is decaying. And then here at about 10 to the 6 years, we find a moment where we can match both the calcium and the aluminium-26 ratio. However, the chlorine ratio is matched approximately over here. And then we see for the 80 solar mass model, we see something similar. So we match the early solar system ratio for aluminium here, and then we match chlorine here, calcium here, and then chlorine is a mass. And for the same for the 40, we don't, for the 40 solar mass model, so the non-rotating star is below here. We don't even get close to matching calcium, unfortunately, and we don't have near enough chlorine to match the early solar system values. So the conclusions so far are that aluminium-26 and calcium-41 can be matched by models with initial masses of 40 solar masses and up. But chlorine-36 can only be matched by masses of 60 solar masses and up. And then also, as you could see here, there is still like a discrepancy in the delay time between the match of chlorine and the match of calcium. So now the question is, how are we going to solve this? And one of the ways to solve this is to look at the nuclear reactions. Because we know that both calcium-41 and chlorine-36 are produced by neutron captures, we checked the rates and the error bars on those rates and decided to experiment with those a little bit. So we used the 60 solar mass model as an example. Again, for this one, the delay time for calcium is about 1 megayear, while the delay time for chlorine is about 0.3 megayear. And the conclusion from this is, if we want to better match the early solar system, we need either more chlorine or less calcium. So, how are we going to do this? So, either we reduce the reaction rate of the main destruction channel for chlorine, or we increase the reaction rate of the main destruction channel for calcium-41. And as said, these are neutron capture rates. So this is chlorine-36. You capture a neutron, you get a proton and silver, 36 out of it. And for calcium-41, the same story. We capture a neutron, you get an alpha particle and argon out. So model 1 is the standard model from the original paper before we start experimenting with the reaction rates. And here we multiply the rates by a factor of 0.5, and this one we keep the same. Model 3 is we keep the chlorine rate the same, but we increase the calcium one, and the final one is where we change both rates. And then you can see that if we reduce the destruction, yes, we get more chlorine, as expected. We also get, strangely enough, a little bit more calcium. If we do nothing, if we change the calcium rate, yes, we get less. And if we combine the two, then we get about what to expect if we change the rates in this way. Normally, rates are not this uncertain, but for the purpose of looking what they do, we had to multiply with quite big factors. So, and then we did the same procedure as before. And then it came out very interesting that model 1 and model 2 are almost the same. So getting more chlorine out of our models did not solve anything. Also, models 3 and model 4 ended up relatively the same, and this means that definitely we have to look a bit more into the calcium reaction rate. So, and also this brought the difference in delay time down to a factor of 1.8 instead of about 3. So that's an improvement. The only question is this realistic? And in that case, we have to look at the nuclear physicists and beg them to remeasure the rates. So the conclusions for this part of the research were that basically rotation increases your mass loss, leading to an earlier increase in the short-lived radioactive isotope yields. Then the highest masses, so 40 solar masses and up, can explain the early solar system abundances for aluminium-26 and calcium-41, but only the most massive models can also explain chlorine-36. And as expected, no iron-60. But also, there's still the binary models, and they might open up more possibilities to explain the early solar system abundances of all 3 short-lived radioactive isotopes. So very briefly, because yes, we're getting to the end. These are results that haven't been published yet on the binaries. So again, we use the same setup as for the previous models, non-rotating, but we evolved the stars all the way up to the core collapse. And here you can see that we have, again, the effective binary yields, which is the average, the maximum binary yield, and the minimum binary yield. Here, these models run into common envelopes, so that's why they get a lower yield. And the only thing that's important here to notice is that because of if we compare it to models that rotate, this turnover, where the binary interactions start to become about as important as the mass loss, becomes earlier. So then we look at calcium-41, but now it becomes interesting because while there's clearly a big increase here, there's also a very big increase here on the lower mass end. And 10 solar mass stars are a little bit more likely to occur than a 60. So, and where at 60 the binary interactions become less important. Also for calcium-41, but also for chlorine-36, the binary interactions stay relevant a little bit longer because this is produced in a later phase. So again, they look approximately the same. They have a dip at about 15 because the effect of the binary interactions on the 10 solar mass star is very strong. So this looks like a slide I already had. Whoops. So yeah, so we still have to look into the effect on the early solar system of the binaries. So this is a list of stuff you could do after this. So as said, the stars are observed to rotate and are observed to be in binary. So you should combine that, but that is very hard. So one of the things that would be interesting is rotation for the primary stars of the binary systems. Also, we only looked at one particular mass ratio, so it's interesting to look at different mass ratios. We have not considered any reverse mass transfer, so mass transfer from the secondary to the primary star, because all the research so far has focused on the primary. There's KC mass transfer, which happens very, very late on in the evolution of the systems. Also, we considered here fully non-conservative mass transfer, which means everything is lost, and that is probably also not a very realistic assumption, so the mass transfer efficiency is also a factor that needs to be considered. Also, the other thing that's interesting is to get supernova yields for the single stars and the primary stars of the binary systems and see how they compare, because most of galactic chemical evolution is based on single stars, but if you put a star through the binary interactions, it is not exactly the same. So this is also the post-processing of the pre-supernova stars, which means that we hope to get the full set of isotopes, because currently we ran with 209 isotopes, and there's many, many more. However, this is not really feasible for a full stellar evolution, and you generally use another code for that. Other thing is yields for the secondary stars, so you can get like a package yield for a binary system. And then, as said, further exploration of the impact on the early solar system. Also, we need to find a way how to get the material from the source into the early solar system, and one of the things that has been suggested is dust formation, which is, again, a completely different thing. Also, we can already see that wind prescriptions and different types of rotational mixing have quite an effect on the yields, so this needs further exploration. And finally, we only looked at solar metallicity stars because we tried to look at the early solar system. But if you want to look at the galaxy as a whole, you would have to look at non-solar metallicity stars, so from very metal poor all the way to supersolar. And that was the last slide. So thank you for your attention.
Thank you, Hannah. Thank you. Very, very interesting talk. Are there any questions, comments, or feedback?
Yeah, so the for the early solar system case, if I understood it correctly, you seem to be looking at one star that is producing all those elements?
Yes, so in this scenario, we're trying is a single source polluter, but it is very possible that it's actually an ensemble. But we needed to start somewhere, and otherwise you will get a lot more complications. So the goal basically here was to see, can we get a single source that can give us all the aluminium-26 we need without giving us iron-60? And then also giving us calcium and chlorine, though both calcium and chlorine also can be there's some input from cosmic rays, so if that ratio is not fully matched, it's okay.
Thank you.
Thank you. Any more questions?
So thank you for the talk. Your assumption is hence that the initial solar system has aluminum-26, which is proven by the meteorites, yes. I think, and no iron-60.
No, there is iron-60 in the early solar system,
yes.
But the problem is that the ratio of aluminium-26 and iron-60 is very different from the ratio that is observed in the galaxy. So this means that there is, in the early solar system, there has to be extra aluminium-26. So the iron-60 in the early solar system can be explained by supernovae. And there's also some aluminium-26 coming with that from the supernova. But the ratio is, and now I'm going to flip this the wrong way around probably. So the ratio that's observed in the early solar system is a factor of 300 different. So this means that we need
any supernova yield. Then any supernova yield.
Well, there is a way to fix it, and it is the so-called proton ingestion in the pre-supernova phase, which is research done by a colleague of mine back from Hungary, and also at the University of Hull. They use proton ingestions in the final phases, so they basically use the magnesium-25 that is produced during the stellar evolution and turn that into aluminium. That is also a potential way to fix it. But we looked at a different scenario.
Okay. And then for the binaries, so I mean, the production itself of aluminum-26 is not impacted. It is just the mass loss, and the effect of the mass loss hence brings it easier or brings it in the wind earlier or later in the evolution.
Yes,
Yeah.
basically yes.
Okay.
There will be some extension of the maze sequence, so you get a little bit more production, but as you can see in the plot, so we have to go back. So the maximum aluminium-26 in the center is actually reached pretty early on. So here you have the same amount as here. So basically, it doesn't make much of a difference. The binary interactions won't really affect your production.
In your models of, I think when you change the reaction rates of calcium and
Yes.
chloride, when you change the calcium reaction rate, the chloride abundance changed.
Yes.
Is that something that you expected? Is that a physical result, or is it just a model quirk?
It's not entirely clear, because part of the problem is that if the neutrons don't go one way, they go another way. So what you basically have is a neutron budget. And if you use a little bit more on one side, then you have less for the other side. So there is some interference in there. So yeah, so it is expected that changing one rate has some effect. Also because these are not the only. So for both of them, so there is also an alpha rate, because if we go back all the way to the beginning, excuse me for the flipping between slides. So if we go all the way here, you can actually see that there's two destruction channels. And here as well. So there's an NP and an alpha, and here's an NP and an alpha, and I only changed the dominant one. However, if you change that one, the other one might actually make up for that a little bit. So you always get these kind of effects. So this one effect is that the other rate might take over a little bit, but also if I reduce this channel, then I will have extra neutrons, and they might actually end up in one of these reactions, because the amount of neutrons that I use remains approximately the same from model to model. So this is why there is some weirdness going on there.
Thanks, Hannah. You alluded in your talk about wind physics being uncertain, and I'm just curious what your mass loss rates were for your stars, and have you looked into updating them in your models?
So for the first set, I used, let me think. I think I used the Jager at Nieuwenhuis and the Jager for the cold phase or the hot phase. I have to look this up exactly. Then Vink et al. And Hamann for the Wolf-Rayet. And then for the other set, Nuges and Lammers for the Wolf-Rayet phase. So that did not make that much of a difference. But what actually is the big thing is that what you saw in the models by Lemonji-Kiefi, where these stars actually move into the dusty winds. So they move a little bit more red, and suddenly you have dust, and your mass loss rate just goes up insane. So these are things that need to be checked. But also, yeah, there's new developments in mass loss rates, so that's definitely something that's interesting to implement into the models.
Yeah, so I'm just curious if you have a feeling for if you factor 2 or factor 3 lower your Vink et al. Mass loss rate, because that's something that people in Leuven are now predicting with their models, that Vink overestimates. What's the main result difference here? Is it going to mainly affect the more massive stars, I would expect?
Yeah, well, at the other hand, as soon as you get into the then I would assume that you enter the Wolf-Rayet phase a little bit later, so that would reduce your
But it's possible that the
yields.
convergence that you have at high mass with the other predictions is less robust?
No,
Or
because
is it to
that
go
is
the other way around?
no, because in the high mass end, and also mind the scale here. It looks very nicely converged, but it is still
Okay.
half an order of magnitude.
Yeah. Okay, thanks.
Mind the scales.
Any other question? The last one, maybe.
Thank you for your talk, Anna. I have two questions. First, I think you mentioned at the beginning that aluminium-26 was an observable, like something we can observe. Is it also the case for the two other isotopes you mentioned?
Both calcium-41 and chlorine-36 are in meteorites as well, so this is all meteoritic samples. That's where we get the data for the early solar system from. However, it's not possible to observe them in gamma rays because their signal is a lot weaker. Aluminium-26 and iron-60 are very nice in that sense. There is some work on new instruments that might have higher resolution, but I don't think they will be able to resolve calcium-41 or chlorine-36 decay.
Okay, and my second question was, do you have data and observation where you can compare your model with, or is it planned in the future to have some observation of aluminium-26 and iron-50?
So the problem right now is that, again, the resolution of the instruments is not high enough to resolve single sources. So what you could do is go, for example, to an area where you know the composition, like we have these blobs that are like here with Orion. You could try and basically analyze the stellar sample of that area and then use the yields and combine that information. That could be done. There's hopes that the new instrument a new instrument will be launched, I think in 2025-ish, that maybe they will be able to resolve single sources, but then still with the uncertainties on the winds, it will be tricky to actually get an exact calibration. It also depends on the internal mixing of the star, so there is a lot of uncertainties there. But yeah, there is work done on this. That would be, yeah. So there's people working on that, trying to basically use a combination of galactic chemical evolution and the radioactive isotopes, and then see if they can match it. But again, it's and then also what you start running into is that basically the time delay between the ejection of the winds and the supernova becomes negligible on the galactic timescale. So those populations that are you could see as separate become mixed, and then the supernova yields will start to dominate over the wind yields.
Okay, thank you.
Okay, thank you very much. So I think we'll leave it here. So let's take Anna again. Thank you very much.